Welcome everyone. This is Murali Krishna, Senior Principal Engineer in AWS Bangalore organization. It's my pleasure to talk to you today in this year's SDC virtual conference. Let me share my screen now. Hi, I'm going to talk about separating storage and compute for search engines. Brief introduction about myself. Been working with AWS Bangalore Charter for last 12 plus years. I've built a couple of AWS services, Amazon Cloud Search and Amazon OpenSearch service. Mainly focused on managed services, Lucene, Solar, and OpenSearch in the last 10 plus years. Prior to Amazon AWS, I was working with Yahoo for multimedia, web search, and desktop search. Main areas of focus included information retrieval, crawling, indexing, and image serving. The agenda for this talk. I'm going to present background on OpenSearch, which is one of the popular open source search engine. We'll talk about its storage structure, what is the need for remote storage innovation in OpenSearch. Some of the design consideration also I will cover, and we'll also go through the future work that are planned in OpenSearch storage areas. Quickly going into the OpenSearch background. OpenSearch is a community-driven Apache 2.0 licensed open source search engine, which can be used for both text search and log analytics. It's very easy to ingest data and search, visualize, and analyze your data once the data is indexed. It's built on top of an information retrieval engine called Lucene, which also powers other popular search engines like Solar, Elasticsearch, and many other product search engines are built on top of Lucene today. OpenSearch is a recent innovation, mainly contributed by Amazon and also many other community partners in the open source. What is it good for? So as I already mentioned, it's good for search workloads and log analytics. In case of search, you can load your data into it in terms of documents. Then you can do rich queries, adjust your relevance ranking. There are language features supported, and you can build your search applications on top of it. For log analytics, we support the OpenSearch engine supports real-time log analytics. The ingested documents are available for query within few seconds. Can also do visualizations, dashboards, and alerting and monitoring on top of the ingested data. Quickly going into the details of the flow in a typical OpenSearch use case. Users can send their data from their servers, whether it is like database rows or logs. You can send this data as JSON via REST APIs into an OpenSearch cluster. OpenSearch cluster is a web server built on top of Lucene, as I explained, and it has REST APIs to receive your data. Data is indexed into the cluster. All fields, the JSON document consists of fields, and these fields are key value pairs, and they gets indexed on the search engine. Using the popular REST APIs, you can analyze and query the data once the data is ingested into the OpenSearch cluster. You can do field matching, Boolean expressions, sorting, any kind of analysis and aggregations on top of the indexed data. Quickly going into some of the details, the internals of OpenSearch. Documents are indexed into what is called a index, search index. Each document is a set of field value, what you call key value pairs, and it has a name and a value. And set of such key value pairs constitutes a document, and documents get ingested to OpenSearch index. Each index is partitioned into what we call shards, and that's the single unit of scaling in OpenSearch. It's a distributed system. OpenSearch is a distributed system with multiple hosts hosting these shards. These shards are partitioned so that it can be hosted in multiple hosts, multiple machines, and it can scale to a really large number of shards. Quickly going into the details of the shards, as I said, each index is partitioned into shards, and there can be multiple such primary shards. In this example, in the picture here, we have 5 primary shards, and all of the documents are partitioned into these primary shards. They also get replicated. Each of the shard gets replicated into one or more replica. You can configure how many replicas you need for your query workloads and for your durability. So each of the primary and replica can get hosted in multiple hosts so that if a host failure happens or a zone failure happens, the data is durable in the other shard, in the replica shard, and the query can, and both the writes and reads can get served from the replica shards. So as I mentioned, all of these primary shards and replica shards gets distributed into set of physical host, and OpenSearch ensures that these shards are placed such a way that primaries and replicas are on different hosts, and they are well distributed to handle the load. In case of node failure, the replica is actually in a different host so that you don't see any failures. The queries and updates go to these shards, and both the primaries and replica will get the updates, and they both will index independently today. Queries can be served from either primary or from the replica based on load balancer algorithms that OpenSearch internally uses. Getting into the storage structure, storage details of an OpenSearch engine. If you consider a single host consists of multiple shards, as I explained. And if you get into a shard, there is segment and a translog. Segment is the Lucene index that I talked about. Lucene is the underlying engine. Translog is the OpenSearch concept, which is a write-ahead log for taking documents so that segments can be created asynchronously for better performance. Each segment is a Lucene index which consists of multiple index file format. Lucene addresses multiple use cases. You can do term query, you can do a range query, or you can do columnar aggregations. It has multiple such use cases, so it's pretty much optimized for each of the use cases. So you can see multiple index file format, which is better suited to each use case. So it's not a single index. Underneath, Lucene supports multiple data structures for improving each of the use case. It is each of the segment is a append-only segment, in the sense once it is written, it cannot be modified. Multiple segments can get merged into a single larger segment for better query optimizations. OpenSearch today, or even Lucene today, prefers a local storage for better performance. You can imagine how much of I/O it has to do given this multiple index file format, given a composite query where you might be querying for a term and for a range and also trying to aggregate on multiple fields. It has to read multiple such file formats. So there's a lot of random IO reads that happens on these index files. So it is both while indexing and also for while reading, it does a lot of IO today. So traditionally, these search engines preferred local storage for optimizing such IOs. Let's also throw the durability angle to it and the redundancy angle to it. One machine is not enough. So the segments and translog also gets copied to the replica node. It can be more than one, as I mentioned earlier. So the documents gets written to one node, to the translog and segments, and the documents also get sent from that coordinator node to the other node, which we call replica node. And again, the indexing happens. The creation of the segments is what is called indexing. That happens on the replica node as well for durability and redundancy. So now we are getting into the core of the talk, which is the need for the remote storage. So we talked about how the local storage based indexing and query works. Why do we need a remote storage? So as I mentioned, durability. Today, it's on customers' hands to, or the user's hands to create multiple replicas, and customers or users can make mistakes. They can configure only one replica. It's possible that, like in case of a dual faults, you will lose the data. So remote storage nowadays comes with a lot of or very high durability guarantees. So by using a remote storage, we can offload the durability responsibility to remote storage. Snapshot backup is an option in the current OpenSearch cluster for durability, but it's not sufficient. Snapshot backup is a periodic activity that can happen in OpenSearch cluster to a remote storage like S3 or Azure storage or GCP, the cloud-based storages. It's a periodic job, like an hourly job or like a daily job. So the recovery point can be like 1 hour old. So you bound to lose some data in case of snapshot restore use case, a snapshot restore solution for backups. So it's not enough. We need the documents to be durable to the last second. Like the last document that we ingested should be available or should be durable, even if the whole cluster goes down. Price per GB is another use case for remote storage. As in the IoT and log analytics world, there's a lot of petabytes of data that gets ingested for log analysis. The cost is really high. The old data doesn't get queried in some cases. So you can cheaply store the old data in a remote cheap storage. Indexing performance, as I mentioned, multiple local copies, this duplicate indexing in multiple nodes. So it's really, really expensive for us to repeat indexing on every node. So you can get better performance with one remote storage. And storage compute separation. So since, as I mentioned, since storage is in the local node, compute and storage are tightly coupled today. It's very hard to separate that out. Independent scaling of reads and writes. As you have higher query workload, you will be doing multiple read replicas. Unfortunately, today's architecture, you also require to do the writes on those replicas. So it's really hard to separate the reads and writes. So with the remote storage, you can actually separate the writes, and you can do a one-time write to the remote storage, and you can copy from there to the replica nodes, and you can decouple the writes and reads that way. Let's get into the remote storage design. So the primary node remains as such. So the documents get sent to the primary node for the indexing, and it writes the translog as I mentioned earlier for faster indexing. And for if the primary node fails in between, the translog is replicated to the replica node also in the earlier case. So it is persisted in multiple nodes. So in this case, translog and segments both gets uploaded to a remote store rather than uploading to a peer node which had replicas in the previous case. What it means is the replica nodes here, node 2, node 3, and node 4 in the picture, they can download the segments from the remote store rather than creating their own indexes. So you can also see the translogs in node 2, node 3, and node 4. Why do we need translogs? The translogs are needed in case of failovers. Imagine a scenario where node 1 fails, which is the one primary node which is uploading the data to remote store. One of this node 2, node 3, node 4 has to be promoted to primary so that it can take the writes. So when it gets promoted to primary, it's possible that it is lagging behind the current primary that went down. So it has to catch up, which means the translog that is there in the remote store has to be applied to the local segments that are there in the replica node. So the node 3, if it becomes primary, it will refresh the translog from remote store and can apply the incremental updates to the segments before it starts to take the writes from the client. So both the segments from the primary node, the segments gets periodically uploaded to the remote store, but the translog writes has to be synchronously uploaded to the remote store. This is to handle a case where if a document is written to translog and if it is acknowledged to the client, it's possible that the primary can go down at that point. So before acknowledging to the client, the documents has to be written to at least to the translog in the remote storage. So we have to do a synchronous write from the primary node to the remote store before hacking to the client here. So challenges of remote store. First of all, performance. As I mentioned, while indexing performance gets improved, there is a hit in terms of latency. Earlier, it used to be a local write or a local read. Now it's a network path in node. Like when you're doing a write, you are going over the network to the remote store. Refresh latency can be explained as write to read latency. When you're writing something and when it is available for reads, it can be a little higher than what it used to be in the old model, because the replica nodes are asynchronously copying the data from remote store. So the time for refresh can be higher. Concurrency is another challenge. In the legacy local storage, each of the primary and replica used to have their own store and their own segments. So there is no concern of concurrent writes. And there's no point of, or there's no need to worry about index corruptions. But in the remote store case, the primary is writing to a centralized location. And when the primary switches over, the replica node gets promoted to primary and it's writing to the it's writing to the same remote translog. So there's a possibility of a race condition here and a need for handling the concurrency, because the primary failover, it involves a complicated leader election process. Who is the leader who can write? And if things gets wrong, there can be two leaders at the same point who can be writing to the same place, which needs to be handled. Failover handshake is another challenge. Like when primary switches to the replica node, the primary has to hand over it cleanly to the replica so that the concurrency problem that I talked about doesn't happen. Recovery time is another concern. In the previous case, the replica node always had the local copy of the index and the local translog, which it was indexing all the time. So it was easy to fail over. When you fail over, all the data is available locally. But in the case of remote storage, the incremental data might have to be fetched from remote store to recover to the latest point. The other challenge is this is a huge innovation that we are doing in the storage area. Things like Lucene engine have not done or in any search engine to that matter, has done such a deep surgeries to incorporate or to support remote storage so far. So this is a really deep changes that OpenSearch project or the team is working on to support remote storage and remote translog in OpenSearch. Going into the remote storage components, what are the pieces that constitute this huge gigantic support for remote storage in OpenSearch? First one is the segment replication. So as I mentioned, in the current system of local storage, the documents gets replicated to the Replica node. We call that doc replication or document replication. In the new model, instead of sending the document, we are sending the segments. It's called segment replication. We can send the segments from primary to replica directly. That also is beneficial in terms of indexing performance, but sending it to remote store and from the remote store, sending it to the replica node kind of decouples the storage that I talked about, and also it can give better durability. It reduces the load on replica node because in the document replication model, the replica node is also doing another round of indexing. So it's really doing double the work. The whole cluster is doing double the work and can use and can use 2x the CPU, or actually like multiple. If there are more replicas, it's the number of indexing that happens is equivalent to the number of replicas, and it gets really expensive. No additional indexing cost, as I talked about, like because you index only once, and then you copy the indexed segments to the replica nodes. The second component is a remote segment store. So once you support segment replication, we are supporting ability to copy the segments into the remote store, which is really low cost compared to multiple local copies of the index. The side effect of the remote store is translog handling. As I mentioned, translog also has to be copied to the remote store so that the primary failure is not a concern anymore. It reduces the load on primary because the primary doesn't have to copy the data into multiple replica nodes. It can just copy it once. Better durability is another advantage of remote segment store. You can just rely on the remote store's durability guarantees. There are multiple remote storage options today, which gives multiple nines durability. Remote translog, as I said, is a byproduct of the remote storage work, and it gives better durability for the transaction log and much tighter RPO or recovery point objective. What it means is instead of relying on a snapshot, you can get the latest translog from the remote store, and given the synchronous write, as I explained earlier, the last document that was acknowledged to the client is guaranteed to be present in the remote storage. So the probability or the probability of the data loss is 0. You can recover all the data that you have ingested. It may not be indexed, but it will be indexed on the replica node once the translog is downloaded. It will replay the transaction log and you will get the old data back. So what are some of the design considerations or the trade-offs? Cost versus performance is the first one. While it is going to be cheaper because of the remote storage and just the one-time indexing, there is a consideration for performance. While it can improve the overall throughput, because of the latency for network writes, the performance can be a little lower if you consider just the API performance. But if you consider the overall, so the second point is the latency versus throughput. The latency can be higher for individual writes, but the overall throughput can be higher. The reason is the overall work the cluster is doing is going down. It's reducing because only the primaries are doing indexing and the replica nodes are not doing indexing, which means you can distribute the current primaries into the multiple nodes and reduce the job of, or reduce the load of each of the nodes, that thereby increasing the throughput. So for an ingestion use case or indexing use case, while the latency can be higher, while the latency while the latency gets regressed, the throughput can be improved like multiple times based on how many replicas you had. So at least a 2x throughput improvement is guaranteed because replicas is not doing any work. Durability versus availability is another consideration. Of course, this is highly durable because every document written is persisted in remote store. But availability can be a concern because of the remote storage dependency. Earlier, the only dependency was the local nodes. Now you are depending on a remote call. So there's an additional dependency in terms of network, in terms of the remote storage availability, and any outages that can happen in the remote storage can impact the availability of the OpenSearch cluster. So that's a trade-off consideration. DocRep versus SegRep. So DocRep is a document replication, segment replication is SegRep. Both of them have trade-offs. While SegRep is better for indexing performance, as I mentioned, like you can copy directly the indexed document, it has a delay in refresh latency. As I mentioned, document replication, each of the document is sent synchronously to the other replica nodes. So your documents are available in the replica nodes immediately. In case of segment replication or the remote storage approach that we just discussed, there is a delay in terms of when our document is available for querying. So there's probably a few seconds, or it's a configurable number of seconds, but it's not as fast as, or it's not as fresh as a document replication use case. These are considerations of the trade-offs while choosing a remote store or segment replications or document replication. So we foresee both the models will exist for longer term. So based on the use case, the clients can decide whether you use a local store or a client or document replication, or use a remote store and segment replications going forward. Future work, really want to talk about some of the exciting stuff that OpenSearch team is working on. So all the three pillars that I talked about, segment replication, remote store, and remote translog, is being developed on the open source. So the GitHub links are provided here: segment replications, remote storage, and pluggable translog. All the three links are provided here. Of course, we are trying to give the framework in the first phase where all these interfaces will be available for anyone to implement. The segment replications is the foundational piece which will allow innovations on top of it. And remote storage will allow multiple remote storage to be plugged in based on the user's preference. Pluggable translog is also going to be a similar options. You can use local translog as an option, or if you prefer, you can use a remote translog. It can be a different remote storage than what you are using for segment storage. For example, you might prefer a Kafka or a Kinesis queue for translog, but maybe S3 or GCP for storage. Customers can configure different storages for translog and segments. We are also thinking of supporting an option in pluggable translog where you can decide no op translog, which means there is no translog at all, which can definitely improve the performance even further. This is usable in case of if you don't need durability within the OpenSearch cluster and you have a durability outside of the cluster anyway. Some of the use cases have a Kinesis or a Kafka queue in front, or a DynamoDB or any other databases in front of the OpenSearch clusters, which already have a persistence layer, which already gives a persistence layer. They are willing to redrive the docs in case OpenSearch has an outage. So in that case, they don't really want a durability guarantees. So for such use cases, we are thinking of improving the performance even further by not doing any durability or a transaction log guarantees. For that, we are thinking of supporting something called streaming APIs, the last point in the slide here. Instead of sending the bulk documents or number of documents into segments into the translog directly, you can just send this to a queue, and the OpenSearch cluster will support a streaming API where the data can be continuously streamed and it will be returned to segments. And anything, if there is a failure, the last commit points will be exposed, and client should be able to redrive from that point rather than relying on OpenSearch cluster. We are starting with S3 as the remote store as the first deliverable. We welcome the community to contribute and integrate other storage solutions into these plugins. Indexing and search separation is one of the future work that we are thinking. Right now, the primary and replica both are serving the reads. It has some challenges if we won't be able to optimize each of the node for a particular use case because both are doing query and indexing. So going forward, since indexing and search nodes are separated is separable now, we are thinking of supporting indexing only fleets and search only fleets. It would give us ability to innovate more going forward for read optimizations and write optimizations, and can use different hardware for different use cases like indexing and search. Another idea that we are working on for future is smart caching. So today, the replica nodes will download the shards from the remote storage fully and serve from the local cache, from the local shards because of the query latency concerns. Going forward, we are trying to even reduce that cost further by directly querying from the remote store, and might do a cache for the hot data on the read replicas. But anything which is a warm data or cold data, we are thinking of querying from remote store directly and cache it on demand on the read replica nodes. We'll go to so that's pretty much it. We welcome any feedback from your side, and wanted to thank you for listening to this presentation so far. There's a contact email ID here, and the OpenSearch website is also given for any feedbacks. And we welcome the community to innovate on the OpenSearch engine. It's an open source engine, and take the storage innovations forward. There are multiple storage innovations that are happening in the industry. You will be listening to many other presenters about the storage innovations, and we welcome the community to integrate those storage engines where it makes sense with the OpenSearch as a remote storage and remote translog going forward. With that, I'm ending the show, ending the presentation here. Also want to thank the SDC conference organizers for giving me the opportunity to present this today. Thank you.